Hi. First of all, I want to thank you to organizers for possibility to present the result of our investigation. I hope it will be informative and interesting for you. The presentation is dealt with application of time-lapse gravity for monitoring of underground gas storage condition and exploitation. In further, I will use abbreviation UGS for underground gas storage. So, time-lapse geophysics is becoming an increasingly important and powerful method to measure, monitor, verify, and predict complex time-varying processes in the Earth. An application includes resource management, hazard risks assessment, environmental issues, and fundamental science questions. Time-lapse geophysics is widely used for studying subsurface process which is changing in time and may influence on geophysical fields. Underground gas storage is object created for regulating of seasonal changing in gas consumption. The main issues for UGS monitoring is understanding of working gas volume distribution within UGS reservoir, prediction of inner wall space, gas pressure, determination of stagnant zones, and working gas migration pathways. The instrument that can help to understand these issues is time-lapse gravity. Gravity is the geophysical method that is sensitive to mass changing. UGS reservoir as petroleum system can be exploited in two regimes. Gas drive, characterized by pressure increasing with gas injection to UGS. In other words, gas density increasing caused increasing in gravity on the Earth's surface. Other one is water drive exploitation regime whereby the gas is driven through the reservoir by an active aquifer. Formation pressure is changing slightly. The gravity change will have an inverse character because replacement of gas by formation water will induce opposite density anomaly. Formation gas has less density than formation water. Exploitation of UGS in both regimes met an influence on gravity which can be measured on daily surface. As we will see in further, time-lapse data gives an opportunity to build 40 models of density, 40 models of gas pressure and gas volume in place, to locate dynamic reservoirs in which working gas can be injected and withdrawn, and to understand gas migration pathways from storage wells to dynamic reservoirs. Time-lapse UGS monitoring is usually performed in inspection wells and via 3D seismic survey, and incorporates 3D models of porosity and permeability, formation pressure, and volume of gas by dynamic modeling. Unfortunately, 4D seismic is rarely available and well data are too sparse to build an adequate reservoir model. That was the case for Dashava UGS located in the Carpathian region of Ukraine. UGS was created in 1972 and comprises of 6 depleted gas pools within 8 and 9 lower Dashavian horizon of Neogen in the Dashava gas field. All gas pools are the parts of one hydrodynamic unit. Dashava UGS is the third largest in Ukraine. Dashava UGS has 5.3 billion of cubic meter of total gas capacity, 2.1 billion cubic meter of working gas capacity. The maximal formation pressure is 5.7 megapascal, the minimum is 1.9 megapascals. The gas drive regime and operated by 100 of storage wells. 27 injection and withdrawing cycles result here and one-third increasing of cushion gas in reservoir. Four seasons of time-lapse high-precision gravity measurements were taken for 2 years. Two series were taken at empty UGS and two series were taken at full UGS. Twofold gravity measurements were provided on 530 stations. The average standard deviation of gravity measurements is 4.1 mkGal. Modern high precision equipment were used for acquisition. After finishing of time-lapse gravity survey, a gravity change map was built. This map is show a difference in gravity between completed and depleted UGS. For map building, all gravity measurements were divided into three classes. Class 1. Gravity field was changed proportionally with storage pressure change. Class 2. Gravity field was changed inversely proportional with storage pressure. And Class 3. Gravity field wasn't changed after gas hydraulic injection. As you can see, near 60% of stations is located within Class 1. These are station near storage well zone. This is logically, but also you can see a peripheral zone with positive gravity change, which indicates working gas movements. But only timeless gravity data is not enough for quantitative interpretation of UGS condition. For this reason, initial 3D density model of the Dashava UGS was built. Initial 3D density model is coordinated with all available geological and geophysical data and has 1 meter depth resolution, consists of 28 of structural surfaces based on 3D legacy seismic data. Input data for model building was also regional gravity data, well data from 108 wells, petrophysics by core gas pressure measured in wells and the period of time-lapse gravity. Rock density is calculated mainly from gamma ray log and spontaneous polarization log if a gamma ray log was absent. You can see an example of rock density distribution with depths from two wells. Initial 3D model described an initial density properties at the moment when UGS was depleted as of 2013. This 3D model was used for further inversion with time-lapse gravity data. For this aim, gravity field for inversion was calculated by adding of gravity field from initial 3D model density to gravity change caused by gas injection in UGS. This field was measured in time-lapse acquisition. The 3D density model was refined by joint full-depth inversion of gravity and well data on a period when UGS was full. Active using of data from wells, in which formation pressure measurements were periodically provided, ensured agreement between 3D density change and well data. Final standard deviation of iteration was 3.5 mkGal, which is equal to time-lapse accuracy. On slide, you can see the result of inversion, the 3D model of rock density change as the result of UGS exploitation. The next stage was determination of dependence between formation pressure change and rock density change in near well space of well with pressure measurements. For this aim, 107 wells with pressure measurements were used. Obtained dependence you can see on slide. Using it, 3D model of rock density change was recalculated to 3D formation pressure change model. Other thing is necessary is knowledge about pore space distribution in which gas can be accumulated. The 3D porosity model using well data was built, and contour of gas drainage of the Dashava UGS was determined using available geological information well data, and reservoir structural surface gradient, which shows boundary of geological structure of UGS reservoir. For quality control assessment, calculated pore gas saturated volume was compared with project value and error was only 1.8%. Approximate 3D models of formation pressure were created using 3D models of formation pressure by wells on depleted UGS and completed UGS, and obtained 3D model of formation pressure change as a result of time-lapse gravity data inversion. Using approximate 3D models, the gas volume was calculated at depleted and completed UGS for adaptation on balanced values. On this slide, you can see calculated gas volume on different UGS stages before adaptation compared with balanced values. Adaptation process was following. Stage 1 was determination of pore gas saturated volume, which can hold balanced amount of working gas using 3D model of formation pressure change obtained by time-lapse gravity data inversion. As a result, areas with formation pressure change higher than 26 and 6 technical atmospheres can hold balanced volume of working gas with relative misfit 0.3%. Gas volume within zones of active gas drainage has 31.1 million cubic meter of gas saturated pore volume, and it is 32% from total gas saturated reservoir gas volume. The rest, 57.6% of gas within UGS reservoir, is less drained and the most likely filled by cushion or remaining gas. Total volume of gas within this pore volume is near 1.5 billion cubic meters. Based on this model, 1.5 billion of gas was equally distributed in less drained zones, taking into account well measurements. For this purpose, scale coefficients were used for approximate 3D models. Final misfit between balanced value is 6.6% in depleted UGS model, 4.2% at completed UGS model. Working gas volume misfit is only 1%. On this slide, you can see maps of gas compactness in lower Dashavian 8 horizon at depleted UGS, completed UGS, and working gas distribution in this horizon. This slide shows maps of gas compactness within second lower Dashavian 9 horizon. This horizon has purest reservoir quality and hold less gas amount compared with thirst horizon. This slide shows 3D formation pressure models on different stages of UGS exploitation within lower Dashavian 8 horizon. As you see, formation of gas pressure has complicated distribution and can be obtained by simple interpolation of well data. Time-lapse gravity gives an opportunity to do this. This is slice of 3D formation pressure model within LD9 horizon. The quality control of 3D formation pressure model was made using real pressure measurements in wells at the period of time-lapse gravity acquisition. For 3D model of depleted UGS, relative misfit was 1.5% for LD8 horizon and 3.7% for LD9 horizon, with great correlation more than 97%. This is quality control of 3D formation pressure model at completed UGS. Result was also great. Misfit were 1.8% and 3.5% for two horizontal with UGS reservoir. As a result of data interpretation, dynamic reservoir within LD8 reservoir were mapped. Yellow color marked the working zone of storage wells, which hold near 50% of all working gas volume. Green color is zones of mapped dynamic reservoirs. There are 6 dynamic reservoirs within LD8 horizon which can take and give back the working gas. Here you can see predicted working gas migration pathways from the storage well to dynamic reservoirs and reverse, and also calculated volumes of working gas capacity within every local dynamic reservoirs. Here is the same for second productive LD8 horizon. There are 4 local dynamic reservoirs were mapped apart from working zone of storage well. Predicted working gas migration pathways from storage well to dynamic reservoirs and reverse, also calculated volumes of working gas capacity within every local dynamic reservoirs. Summary prediction for Dashava UGS reservoirs is following. 10 local dynamic reservoirs were mapped within 2 production horizon. 65.5% of working gas is located within working zone of storage wells. 29.8% of working gas is located within predicted local dynamic reservoirs. Working gas volume within all zones and within every dynamic reservoirs were calculated. Working gas migration pathways were predicted. 4D model of formation pressure and gas volume compactness were built. At the end of the presentation, I want to summarize technology workflow of time-lapse gravity for UGS monitoring. First of all, it is necessary to execute not less than 4 sessions of identical time-lapse gravity acquisition on different stages of UGS exploitation with modern high-precise equipment. The next stage is regular and special time-lapse gravity data processing with station classification procedures. Initial 3D density model should be created with further 3D linear inversion of gravity data with geologically conventional limits on rock density change and active using of well data. After inversion performing, relation between rock density change and formation pressure change should be determined. And approximate 3D models of formation pressure on different stages of UGS exploitation should be calculated. These models should be calibrated using real UGS data about balanced values and formation pressure. Geological prediction based on obtained models should be the final result of time-lapse gravity. At the end of 2019, there were 661 UGS facilities operated in the world. The global working gas capacity reached 422 billion cubic meters. The safe and effective performance of UGS may be based on understanding of the changes in the properties of storage reservoirs, physical precondition and practical application result of time-lapse gravity measurements and interpretation allowed increasing the efficiency of UGS exploitation. Thank you for attention, and it will be a pleasure to answer your questions.